Hello, today's lesson's on concavity. We're dealing with the second derivative today instead of the first. Our last lesson dealt with the first derivative, and we said if the first derivative is greater than 0, your function is increasing. And we said if the first derivative is less than 0, it's decreasing. Today we're going to learn why when you take the second derivative and it's greater than 0, it's concave up. And if you have the second derivative is less than 0, it's concave down. Okay, so it's concave up, it's greater than 0, concave down, less than 0. Point of inflection. Point of inflection is when the second derivative is 0 or it does not exist. It's undefined. Okay, and your second derivative has to change from positive to negative. Then you have a point of inflection. Okay, so you're going to set your second derivative equal to 0. That's your point of inflection, possible point of inflection. Then you check, okay. If the second derivative changes sign, you have a point of inflection, which means the concavity changes. Concavity changes at a POI. Okay, so here's my graph. It's concave down, and it switches, and it's concave. It's concave up and switches to concave down. It's somewhere between here and here, okay? So it's concave up, it's concave down. The point of inflection is where it switches, all right? So you're supposed to find the first and second derivative. You're going to set them both equal to 0 because you want critical points, okay? If f prime changes from increasing to decreasing or vice versa, you have a max or min, okay? Your f prime is equal to 0. This f double prime is equal to 0. It crosses the x-axis, it's changing from positive to negative or negative to positive. All right, so we're going to work a couple of these. Determine the point of inflection and discuss concavity. First derivative, x squared. Second derivative, 2x. 2x equals 0, x equals 0. We're going to go back to making those charts. Yes, you're going to make the chart. You're not going to get lazy. You're going to fill it all in. You're going to find a point and check it. So I'm going to try -1. You get -2. It's negative. F double prime of 1. You get 2. It's positive. So here it's concave down. And here it's concave up. Okay? Since it changes from negative to positive, x equals 0 is a point of inflection. Alrighty? Do it again. First derivative, 6x squared minus 6x minus 12. Let's pull that 6 out of there. Well, it doesn't matter. We got to do the second derivative first, so let's do the second derivative. Why not? Then we'll factor. So then the second derivative is 12x minus 6. And you set it equal to 0, so you get x equals 6 over 12, which is a half. Now my interval, is that the only one? Yeah, makes sense to me. We'll talk about that, why that makes sense in a second. Alrighty. F double prime of 0 is -6. F double prime of 1 equals 6. Concave down. Concave up. Let's back up to the first derivatives and solve it. You factor out the 6 and you get x squared minus x minus 2. That factors to x minus 2 and x plus 1. So you got x equals 2 and x equals 1. So if I'm going to graph this puppy, it's telling me at, this is negative 1. At negative 1, there's a min or a max. Okay. If I plug in negative 1 into here, what am I going to get? Let's do it. Negative 2 minus 3 is negative 5, plus 12 is 7, so it's 12. It's up here. All right. You plug in 2, what do you get? 16 minus 12 is 4, minus 24 is negative 20, so it's negative 15. And this is a half. All right, so my graph, I know it's an x cubed with a positive leading coefficient, so it goes up and comes down and goes up. Okay? From using my first and second derivative, I found a max and a min. My point of inflection's at a half. It's concave down and it's concave up. And that's what my thing told me. It's always a nice idea to sketch it, see if you were right. Okay? Do you have to do all that? No. But hey, apply what you know. Use your brain. Thinking powers. Okay? Let's do one that's a little different. Okay, let's rewrite this. 6 times x squared plus 3 to the negative 1. So your first derivative equals negative 6 times x squared plus 3 to the negative 2 times 2x. Negative 12x over x squared plus 3 squared. Now I'm supposed to do the second derivative. So you do low, oh man, d high minus high, d low. Ooh, it's not going to fit. Back up over here, x squared plus 3 squared, negative 12 minus negative 12x times d low is 2 times x squared plus 3 times 2x, shoo, over x squared plus 3 to the 4th. Well, that's ugly. And we got to set it equal to 0, so we have to set the top equal to 0. Well, let's see. You can take out this and one of those and one of those. So now I have negative 12 plus 12x times 2 times 2x over x squared plus 3 cubed. Alrighty. Oh man, this is a tough one. They didn't give us enough space. So what's this? 2 times 2 is 4 times that's 48x squared. So 48x squared minus 12. Got to set that equal to 0. So x squared equals 12 over 48, which is 1/4. So x is equal to plus or minus 1/2. What makes it undefined? Nothing, because this will never be negative. So now your chart's going to go from negative infinity to negative 1/2, negative 1/2 to 1/2, and positive 1/2 to infinity. This is all for that problem, guys. Cheep, cheep, cheep. And we're plugging this into this, right? So I'm plugging it into 48x squared minus 12 over x squared plus 3 squared. Well, let's plug in a negative 1. So you have 48 minus 12, which is 36, over 4 squared, which is 16. So that's positive. F double prime of negative 1. Let's try 0. You get negative 12 over 9, so that's negative. And you plug in 1, you get 48 minus 12 again over that, so it's positive again. So you have it changes from positive to negative, so that's a point of inflection. It changes from negative to positive, that's a point of inflection. So its concavity changed twice. So this is up, down, and up. Shoo-wee. That's messy. Sounds like something I'd ask you on a test. Alrighty. Determine the point of inflection and discuss the concavity. Alrighty. So my first derivative is 2/3 x minus 1 to the negative 1/3. And my second derivative is negative 2/9 over x minus 1 to the negative 4/3. Negative 2 over 9 times the cube root of x minus 1 to the 4th. So x equals 1 makes it undefined. The question is it in the domain? Yes. Okay. Sounds like it's not differentiable there because it's undefined, but it's in the domain, so, and it's defined, so it could be a point of inflection. So let's check. Negative infinity to 1, 1 to infinity. Let's try f double prime of 0. If I have negative 1 to the 4th, that's 1, so that's 1. That's negative 2/9. That's negative. If I do f double prime of 2, is that going to work? Oh, yeah, good. So it's 1. So it's still negative 2/9. Ooh. It doesn't change signs. So it's not a point of inflection. Huh. You think that's true? Let's look at the graph. I'm going to graph it. Hang on. I'll put it in my calculator. I'll draw the picture for you. And what am I graphing? Parentheses x minus 1 raised to the 2/3. I drew a picture. Window, standard, exit, draw. Ooh, it is always concave down. You know what the graph looks like? It goes like this. It goes whoop, whoop. That's cool. Yeah. So at 1, it's not a point of inflection because it doesn't change concavity. It's not differentiable because you got a sharp point there. That's fun. It's the things we learned about a function. Concave down. Not a point of inflection. All right. Use the graph below to determine critical points. All right. Critical points. Minimum. Point. Concavity changed. Okay. It's the POI and a min. Min. Does it have a point of inflection? It looks like it's pointing up and then flips over. Maybe right there. That's the eyeball. Those are bad graphs. Critical points, point of inflection. Min, max, point of inflection. Change concavity. All right. Now, the intervals in concavity go from points of inflection. So we're going to guess it's at 0, and we're going to guess this one's right there at 2.7. Okay, so x equals 0 and x equals 2.7 are POIs. I eyeballed them. All right, so you're going to say it's concave up, negative infinity to 0, and 2.7 to infinity. And it's concave down from 0 to 2.7. Notice we're only using the x values, not the y's. Only x's, only x values. Okay. And the POI are endpoints of intervals of concavity. Min and max, endpoints of increase, decrease. Okay, so like here, it's increasing from negative 2 to 2, and 3.5 to infinity. It's decreasing negative infinity to negative 2, and 2 to 3.5. Again, we just use the x values. These are the min and max, the POI. Okay? Keep that straight. Only x values. All right, here's another one. I want to let you do that one by yourself. They gave you this point. We're going to assume that was the POI. Put another one right there. I don't know, put it right there and make your life easy. Okay? And we'll say this one's right there. Ooh. This is the graph of the derivative. Oh. These are your now we have to talk about it. All right. The graph shows the graph of the first derivative of a twice differentiable function on a closed interval. On what open intervals of the function above is it concave down and increasing? This is the first derivative. Okay? This is where the first derivative is 0. Okay? This is where the first derivative is 0. So if it's increasing, it has to be between those points, and the first derivative has to be positive to be increasing. Well, it's positive here and here, so you can go negative infinity to 2, and then 2 to, what is that? Is that 2? No, that's 2. This is, I don't know, 1. Let's call it 1, 2, 3, 4. Sorry. That point was 2 point something. This should be 1. Okay? And it also increases from, that's 1, 2, 3, 4, 5, 6. 6 to 8. All right? It decreases when it's negative, and that's only between 4 and 6. Okay? Concave up. Well, didn't get that far yet. Point of inflection is when the second derivative is 0. The second derivative is the derivative of the first. So here it's a horizontal line there, there, and there. Did I change from, did it change signs? Did it cross the x-axis? Ooh, I don't know. All right, POIs are going to be at x equals 1, 3, and 5. Maybe. That was tough. Okay. All right, last one. Oh, yeah, perfect. All right, determine from the graph whether f possesses extrema on the interval, closed interval a to b. So they're talking about this point right here, and this is the graph. The graph's concave down, so what do you know? F double prime at 1 has to be less than 0. F of 1 is equal to 0. The function's increasing, so f prime of 1 is positive. So if you put those in order, it has to be f double prime, then f, so it has to be d. Think about that. This is concave down. This is, read off the graph. This is increasing. Tough stuff, wrap your head around that. And they asked us a question up here too. They wanted to know on what open intervals is the graph both concave down and increasing. So it has to be increasing, so it has to be up here. And the second derivative has to be negative. The second derivative is the slope of these. So concave down and increasing. It's increasing because up here. Okay, so these are my choices. This, and this. Because my first derivative, that makes it increasing. All right? To be concave down, the second derivative is negative. That's the slope of, slope of f prime. So I've got negative slope here and negative slope here. So my intervals are from 0 to 1 and 3 to 4. Ooh, that's a good problem. Hurt your head. Think about that. That's really our next unit. But I'm glad they put it on here. Starting to tie it all together. Okay? That's all I got for you. Go practice. Make your second derivatives. Make your chart. Write your sentences. Justify using calculus.